Your application works perfectly with 10 users. It still works at 100. At 10,000, it starts to slow down. At 100,000, it falls over. This is the scaling problem, and it's not a bug, it's a consequence of the system's architecture. Every architectural decision you made when traffic was small has consequences at scale. The good news is that scaling is a well-understood engineering discipline with a clear conceptual framework. The bad news is that naive scaling decisions create new problems faster than they solve old ones. The book draws on The Art of Scalability by Abbott and Fisher to introduce what they call the scale cube, a three-dimensional model for thinking about how applications can be scaled. Each axis represents a fundamentally different approach to handling more load. The x-axis is cloning, run multiple identical copies of your application. Each copy handles a fraction of the traffic. This is the simplest form of scaling and should almost always be your first move. The relationship is linear, double your instances, roughly double your capacity. Node.js is particularly well suited to x-axis scaling because Node.js processes are stateless by design in most architectures. The y-axis is decomposition by function. Split your monolithic application into separate services, each handling a different part of the business domain. User service, payment service, notification service. This is what the term microservices refers to. Each service scales independently based on its own load profile. The z-axis is data partitioning. Different users or datasets go to different instances. Shard your database, users A through M go to shard 1, N through Z to shard 2. This is the most complex form of scaling and is typically only warranted at very large scale. Understanding which axis to scale along and when is the core judgment call of distributed systems architecture. The scale cube isn't just a theoretical model, it maps directly to real architectural decisions you make in production. Let's follow each axis to its concrete implementation. X-axis scaling with Node.js has a specific challenge that the book highlights immediately. Node.js processes are single-threaded. A modern server with 16 CPU cores runs 16 simultaneous JavaScript threads, except it doesn't, by default. A vanilla Node.js application uses exactly one core. The other 15 sit idle. This is genuinely wasteful. Your 16-core server is running at 1/16 of its CPU capacity for Node.js workloads. X-axis scaling solves this by running 16 Node.js processes on that machine, one per core, and distributing traffic across them. You get to use all your hardware. The Node.js cluster module and process managers like PM2 are the tools for this. Y-axis scaling, microservices, is more complex to implement but enables independent scaling of different parts of your system. If your image processing service is at 100% CPU but your user authentication service is at 10%, you can scale the image service without touching authentication. You can redeploy the payment service without redeploying the rest of the application. These are powerful operational advantages. Z-axis scaling is often the least well understood. It's particularly powerful for multi-tenant SaaS applications. You can route each customer's traffic to a dedicated instance, guaranteeing isolation and preventing one customer's load from affecting another's. Geographic routing is another Z-axis pattern. Route European users to European data centers, American users to American data centers. Most production systems use all three axes to different degrees. Understanding the model means you can look at your traffic patterns and choose which axis to scale along next, rather than defaulting to add more servers without understanding what that actually achieves. The specific gap that makes scaling Node.js applications on a single machine non-trivial is worth lingering on, because it's often misunderstood. The V8 JavaScript engine is single-threaded. This is not an accident, it's a design choice that eliminates an entire class of concurrency bugs. You never have to worry about two threads mutating the same data simultaneously, because there's only ever one thread executing JavaScript. The event loop, callbacks, promises, all of this is single-threaded execution managed by a single JavaScript runtime. This means that on a 24-core machine, one Node.js process uses roughly 4% of available CPU. The other 96% is idle, doing nothing. For I/O bound workloads, web servers that spend most of their time waiting for database responses, this isn't a huge problem. A single Node.js process can handle thousands of concurrent I/O bound requests efficiently because while one request is waiting for a database response, the event loop services other requests. CPU is rarely the bottleneck. But consider a compute-intensive request, generating a PDF, processing an image, running a complex calculation. That computation monopolizes the single-threaded event loop, blocking all other requests. With multiple processes, that computation happens in one process while other processes continue serving traffic normally. There's also the resilience argument. A single process represents a single point of failure. One unhandled exception, one memory leak that causes an out-of-memory crash and your entire application is down. Multiple processes mean that a crash in one doesn't affect the others. This is the argument for x-axis scaling at the single machine level: use all your cores, improve resilience, isolate failures. The cluster module is the built-in Node.js mechanism for doing exactly this.